Well, hello, I'm Aldo Porco, and I'm going to present you automatic reduction from from pH into strips, or how to generate short problems with very long solution. This is a joint run with Alejandro Machado and Blay Bonet, and we are from University of Montpellier. Okay. A brief recap from ICAPS. In ICAPS, we presented a software tool that allows us to translate NP decision problems written in second-order existential logic into a strip problem. We offer some guarantees, some strong guarantees, such as if the input problem is positive if and only if the strip problem has a plan. The translations runs in polytime, which means that we're doing a reduction from the NP decision problem into the strip problem. Also, the strip problem is decidable in non-deterministic polynomial time, which means that our approach is not an overkill. And finally, if we have a plan for the strip problem, that means we can construct a solution from the input problem. How does our software tool works? Well, it takes an input signature that contains the relational symbols, a second-order existential formula that encodes the NP problem, and finally a finite structure that encodes the instant of the decision problem. As an output, it gives two PDLs, one of the domain and one of the instance of the problem. We gave some guarantees that it runs in polytime for a fixed signature and formula, and the output is no harder than the input in the worst case. Well, our contribution with this paper, where we're tackling all the polynomial time hierarchy instead of only NP. The generated problems are general strip problems. The translator still runs in polytime, and we did some experimental evaluation over some difficult instances. What use can we have with our tool? Well, we can leverage the technology to NP problems and design new benchmarks for planning, to test planners and heuristics too. Well, I'm going to give a brief explanation of what is the triptych complexity theory that I'm going to call DCT, and what is the polynomial time hierarchy. The DCT studies theory from a logical point of view instead of doing any commitment to a model of computation, like lambda calculus, Turing machines, etc. The major of complexity classes has been already characterized with a fragment of logic that corresponds to it. Some achievements of the DCT are, well, a non-deterministic closed state is captured by second-order axis plus crump. P is captured by second-order axis Horn, and P is captured by second-order existential logic. PH is captured by all the second-order logic, and PH is captured by second-order existential second-order logic, and P space is captured by second-order and a tricyclic closure. What is polynomial time hierarchy? PH. It's an infinite hierarchy of classes that contains P, NP, NP, to NP, NP to NP to NP, etc. And there's so many ways to define pH, but we're going to define it using oracles. Well, pH is the union of all sigma k, where sigma 0 equals P, sigma 1 equals NP with an oracle of sigma 0 that's equal to NP with an oracle of P that is equal to NP. In a more general way, we have that sigma k plus 1 equals NP with an oracle of sigma k. We also know that pH is closed under complementation, so we know that co-NP and all the pk for the case major or equal to 0 belongs to pH. It also is believed that pH is different from P space, otherwise pH is equal to some sigma k. A canonical problem in sigma k is decide the validity of a formula in that way, and intercalate quantifiers of second order beginning with an existential. Well, some results. The first result, we're tackling a problem that's in sigma 3. It's a exist for all exist problem, the second order part, with 150 clauses. Let's watch some setup. We have here the first existential with 30 variables, the for all with 2 variables, and the innermost existential with 30 variables. For each setup, we ran 5 instances, and in this setup, for example, all of them were negative. That means there's no plan for the strip problem, and with an average time of almost 1 hour. And finally, the input in kilobytes of the video was of 18 kilobytes. And these were solved all with the returning set-based plan, and Llama 11 does not perform well with this kind of problem. As a counterpart, we have not recoloring. That means the ones that are positive are the graph that cannot be colored with 3 colors. And this is pi 1, it's going P. We run 5 random graphs for each number of vertices. As an example, we have here a graph of 4 vertices. We run 5 instances. 1 is positive and 4 negative. The negative one means that it can be 3 colored. And the average time of the positive and the average time of the negative is seconds. And the length of the plan in steps, the steps needed to reach the plan. And finally, the input in kilobytes of the problem. As you can see, M does not perform well with this types of problems, but Llama performs really well. In fact, we had a result in which Llama reached a plan with 400,000 steps. That's a lot, and only with a little input, that 1 kilobyte. Well, you might say, your plan can go straight to the point and does not have a branch factor. Well, that's not the case, because we ran the same problems with blind search and does not perform well. As you can see in this one, the time is 1,800 seconds, and for the other one, the time was 0.1 seconds. Then that's not the case. As a conjecture, we said that Llama 11 solved this instance because of the implicit serialization of subcodes enforced by the multiple queues. Well, so to show some examples, we have SAT and USAT. These two problems are defined over a vocabulary of 2 relations of RT2, P and N. P says that a variable appears positive in a class, and M says that a variable appears negative in a class. So, what is SAT? In SAT, we are trying to guess an interpretation of T. T is a truth value of the variables, where for all the class, at least one variable makes it true. As a counterpart, we have USAT, in which we need to prove that for all interpretation of T, at least one of the clause is negative. In this example, there's an instance of SAT, and the instance is satisfiable with this model. And the plan that generates the planner is a plan like this, in which we first have a guess part, in this case empty because all set to negative, and then a part in which it proves each of the clauses. 3 clauses, one here, and one here. Then an example of USAT, in which we need to prove that for each interpretation, as we can see, we begin the part of the quarrel and we prove it for the first interpretation. Then by some mechanism we switch to another interpretation and prove it, and for 2 variables there are 4 interpretations, and it's good. Well, the outlet of the translation. For the first order formula, fluents represent the validity of formulas, and operators establish the validity of the formula from the validity of the subformulas. For the second order existential quantifier, the plan chooses an interpretation, and the plans move to prove the validity of that formula. And finally, for the second order universal quantifiers, the plans iterates over the interpretation and proves the validity for each one of them. Well, what's the idea behind the iteration over all the interpretations? Well, let's consider an unary relation T over an universe of n object. There are 2 power n different interpretations of T that can be identified with 2n different words, and we said that the if elements of T, the if elements belongs to T interpretation if and only if the if bit in the word is 1. What are we doing? Well, we are iterating over the words, starting at 0, 0, 0, 0, and adding 1 each time till we have 1, 1, 1, 1. For a general case, if we have a relation of k-arity, the word will be of n per k, the length of the word. Well, how to capture p-space? We know that p-space equals the second order existential plus a transitive closure. The transitive closures operator denotes the connectivity on a graph defined by the formula. If we use the fluent to denote the validity of the formula, then we can design the actions to prove the validity of that operation, the transitive closure operation. Therefore, implementing the transitive closure in strips is straightforward. It just finds the paths on a graph whose edges are given by the fluents. Finish a summary. We extended the tool presented in ICAPS 11 to tackle pH instead of only MP. It implements a system that permits more efficient translations. We perform experiments that are interesting for Lab 11 that was not before. And the tool can be used to design benchmarks for test planners and heuristics. And finally, the tool can be extended to target the whole spin space without much work. Well, thanks a lot.
Thank you.